In this session, we're going to talk about correlation. Underlying the concept of correlation is the idea of covariation. And in this context, covariation simply means that as one variable changes, so does the other, in a systematic way. Now don't get this confused with causation. With correlation, we can't say definitively that one variable leads to a change in another variable. Instead, we can simply say that they seem to be related in some way. Now before getting into the statistics, we can visualize the data using a scatter diagram. And with the scatter diagram, essentially what we're doing is we're taking two variables, an x and y variable, and we're graphing them in a two-dimensional space. And for example, here we're looking at the relationship between GPA and shoe size, or specifically we're looking to see if there is a relationship between GPA and shoe size. Each of these dots represents a given individual and participant, and it looks like there is no relationship here. You see how there's a big circle, and so we have some people that have both small shoe size and a low GPA, but also some people with small shoe size and a high GPA. So apparently there's no relationship between these two variables. On the other hand, this scatter plot suggests that there is a relationship, and more specifically that there is a positive relationship. As one variable increases, so does the other. On the other hand, here's an example of a hypothetical negative relationship. As one variable increases, as the student surfs the web more in class, their GPA goes down. So as one variable goes up, the other goes down. So this is another example of a correlation, in this case a negative correlation. Now here's a third type of example of a relationship between two variables, but correlation isn't going to be helpful here. Correlation is really focused on linear relationships. In this case, in our hypothetical example, there's a curvilinear relationship. And actually this isn't just hypothetical. There's some research suggesting that as income increases, happiness does increase to a point. But once our basic needs are met, then that relationship flattens out, and some researchers actually suggest that happiness goes down with the pursuit of greater wealth. Regardless, the point is that we can have a relationship between two variables that is curvilinear. But with correlation, we're looking specifically at linear relationships. But this is a good example of why you'd want to inspect the data first, because it would not be accurate to say that there's no relationship between two variables just because they are not correlated. So when we look at correlations, we can measure the strength of a correlation using a Pearson correlation coefficient, also referred to as an R value. The Pearson R value is going to vary between -1 and 1. The bigger the correlation coefficient, the stronger the level of association. So for example, in the prior scatter plots where I had either a positive or a negative relationship, as the Pearson correlation coefficient R approaches 1 or -1, you would expect all of those dots to actually fall on one of those diagonal lines. But if the dots are close to the line but kind of scattered around it, then we're going to have some sort of a Pearson R that's between 0 and 1. So one of the things that we can do when we inspect the R values is make some statements about the relative strength of the correlation. So here's a simple table that gives us some guidance on how to do that. Be cautious, however, because context matters. If you were dealing in the physical or hard sciences, you might actually expect a much higher correlation coefficient before you make statements about a strong relationship. On the other hand, in the social sciences, sometimes if we find a correlation of only 0.3, for example, we might be very happy even though this table suggests it's weak. So this is a good starting point, but again, the situation, the context matters when we interpret these correlation values. So, some final assumptions about the Pearson's correlation coefficient before we move into an example within SPSS. First of all, we're dealing here with what SPSS refers to as scaled data, or what you know as interval or ratio scaled measures. We're assuming that the relationship is linear, but we want to inspect it first to see that. And we're assuming that each of the variables on its own is normally distributed. So let's go ahead and look at a specific example. And we're going to use our rent data again, and I'm going to focus on two variables. Decor 1, which is the question asking participants to agree or disagree that they enjoy the decor design of their apartment, and Decor 2, which asks whether or not their friends would be envious of the design of their apartment. So intuitively, you'd expect these to be related. If I like the inside of my apartment, I probably expect that my friends would like it too. The first thing that we can do is visualize the data using Graphboard Template Chooser. I've selected my two variables. SPSS recommends a series of different plots. I'm going to use a bin scatter plot, which is similar to what we were just looking at a second ago. So here's a plot of the relationship between D1 and D2. The darker the circle, the more data points are actually overlaid on that specific point. In other words, we had at least 6 participants who rated the decor of their apartment as only a 1, and they thought their friends would rate it pretty low as well. On the other hand, we had quite a few that rated the decor of their apartment high and thought that their friends would rate it high as well. Hopefully what you see here is a pattern of a positive relationship between measures for D1 and D2. Now, is it significant? We can find that out by using Analyze, Correlate, Bivariate. I've chosen my two variables. The default is to get the Pearson R. You want to make sure that this is selected right here. So let's go ahead and run it. And before I interpret this, I want to help orient you to this table. With the correlation matrix, in this case it's pretty simple because we only have two variables, but with the correlation matrix in general, we'll see one of these again later, you have the variables across both the top as well as along the side. And so we're looking at the relationship between D1 and D1, which obviously are perfectly related since it's the same variable. So we get a correlation R of 1, and the relationship between D2 and D2, of course, is a 1 as well. And then in these other corners, the upper right and lower left, we see the relationship between D2 and D1 and between D2 and D1. So this is symmetric about this axis right here. So you can either inspect the upper right or lower left. I'm going to focus on the upper right. There are three things that you want to do when you look at a correlation table like this. First is to determine whether or not the relationship between the variables is statistically significant. In this case, it is. We can say that there's a highly significant relationship. It's significant at a p less than 0.001 level. That's the first thing you want to check because that gives you the green light to go ahead and look at the Pearson correlation. Otherwise, the Pearson correlation isn't really relevant. Second thing you can make a statement about is the nature of the relationship. In this case, there's a positive relationship as indicated by the positive value, 0.648. And the third thing that we can say is it's a relatively strong relationship by virtue of the 0.648. Thinking back to the table where we had the relative strength of different relationships. So again, three things to look at. Is the relationship statistically significant? Is it positive or negative? And what is the relative magnitude of that value?